All right, welcome everyone. We would like to get started with this advanced 3D features session for the JavaScript API 4x. Thomas from the Esri R&D Center in Zurich, and
I'm Jesse, also from the Esri R&D Zurich.
Yep. And to give you a broad overview of what we're going to cover today, we're going to do an introduction to 3D, which will repeat a couple of steps that were already shown in other sessions, but just to give you a good idea of how things are built. If you missed some of those sessions, we're going to repeat it. So foundations on the 4x API, how we built it, and working with the 3D SceneView in particular. And I will finish off with adding custom graphics to the SceneView, and then hand it over to Jesse, who will show us how you can further customize your 3D visualizations if you choose to do so. We're excited to show you the new custom mesh functionality that we built into 4.7, which will release in April, and then another iteration on external renderers, which have been available for quite some time already, and then advanced camera control that will actually make you do things that you cannot do with just the stuff that I'll be showing you. All right, so let's get started. Foundations for the 4x APIs. So one of the most important things that we did for 4x is that we have a unified data model now that is shared between 2D and 3D, which is very neat because everything you do for your 2D visualization, you can port it to 3D with very little effort. So the map is our main data container for 4x API, and a map consists of layers, which are the fundamental map components, as you might know, feature layers, scene layers, those things. And every layer has a renderer that tells the API how to visualize things available in that layer, and the render itself is composed of symbols which have specific visualization instructions for data items found in that layer. Then we have the common view subclass between 2D and 3D, which is what I was referring to before. So a map view will give you a 2D visualization of your map data that you loaded, while the scene view will create a 3D visualization for you using WebGL and rendering everything on screen. This separation makes it super easy to transition between 2D and 3D, as I already pointed out. But to make use of 3D efficiently and effectively, you need to understand a couple of core concepts, and I would like to go over these now with you. Okay, so to illustrate what I meant, this is a snippet example here. Creates a map. I assign street space map and load a feature layer that shows like states in Germany. And on the left hand side I have a 2D view. So here is my 2D map view, while on the right hand side I do have my 3D scene view. I link these two together so that when I move one, I also move the other. And that's the neat thing about 4x for sure, that the same map data model serves these two visualizations. All right. Then the API uses promises to model asynchronous operations. Certain classes are promises themselves, like for example the scene view or the map view, also layers. As you might know, promises are chainable, and they allow you to actually manage the asynchronous kind of overhead that the web incurs on us. So this snippet here tells you how we deal with that. So when we have a new view, we want to wait until that view is ready for us to work with it. We do that with the view.when. We changed this recently, so it used to be view.then, but since we ran into problems with promise compatibility, we needed to make these classes that are promises themselves use .when instead of .then. So, but you can read up on that on the SDK. So here we wait for the view, then we load a layer which returns a normal promise. So we can use the .then to wait for that layer to load. And then we take that layer, its full extent, and use the geometry service to project it. This again returns a promise. We need to wait until that async operation is done. And then once we have the projected extent, we can use it and tell the view to actually navigate to that extent, which again returns a promise, and that promise resolves once the animation, the go-to animation has finished. All right, so let's get on with 3D concepts. So this is a highlight of a bunch of properties and methods of the SceneView, which is that 3D visualization component in the API. So we have a camera that controls your viewpoint of the current scene. We have this go-to function that allows you to programmatically navigate to a specific viewpoint. We have constraints that allow you to control where you can go in that current scene. Then we allow you to define the padding on the scene view if you want to embed our component into other DOM elements to make it kind of fit in nicely. I also want to briefly touch later on the quality profile, which allows you to basically tell the API how it should render, which kind of quality it should strive for, and also control resources. Of course, if you render with lower quality, you use less resources. I won't touch on two-screen and two-map conversion methods, but we use those to create a screen coordinate from a map coordinate and vice versa. All right, so let's take a closer look at the camera definition. Camera's main properties are the position, which is a point, so X, Y, Z coordinate basically. The heading, which tells us in which direction azimuth we're looking at currently, or we want the camera to look at. So it's north clockwise 360 degrees, so north is 0, east 90, and so on. And the tilt, which tells us how shallow the angle that we want to look at the Earth or at the map should be, where 0 is straight down, 90 horizontal, and so on. All right. So in this example here, I would like to show you how we can control the camera of a scene view. So in my first line here, I clone the current camera. I increase the heading by 5 degrees, which will make it turn to the right. And I assign this cloned camera to the view camera. And let's see what it does. So I click, 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 and start looking towards the right. All right, so programmatic view navigation with the SceneView go-to allows you to do many things, and one of them is to bring the camera to different targets, like another camera or a geometry or a set of geometries, which will make the camera frame all of those geometries, a graphic or a set of graphics, again, framing all those graphics. We support specific desired scales and positions and headings and tilts, as you would expect. And it allows us to also specify what kind of animation we would like, if we would like an animation at all, or if we want to go there immediately. The speed factor and duration and easing. As you already saw and as already mentioned, the go-to returns a promise, and that promise resolves once the animation is finished. Okay, so first example for view navigation, I have my trees here, so my set of graphics. I tell the view to go to this target, which are the graphics, and I also set it that I want it to be at a scale of 5000 with a heading of 30 and tilt of 60. Let's do that, and you see heading and tilt scale as desired. So you can also create smooth animations by specifying the the animation property. In this case, we say that we want to go to a heading that's 30 degrees more than the current heading. So I get the current heading from the current camera, increase it by 30, and tell the view to animate to that heading. So let me execute that. This is how the go-to looks like in this case. And my third example, I would want to show the animation options that we can use to control the easing. So in this example, I don't want to go into too much detail here, but again, clone the camera, increase or change the camera properties, in this case the longitude, and tell it to use the easing function that I specify. You could chain this. I did it such that I have to click 3 times, and the first example will do a linear easing, which is, as you expect, pretty abrupt in the beginning and the end, and linearly interpolated in between. Then in-out cubic, and in and out exponential. One more time, because it looks nice. All right. Then the next thing I would like to talk about are the view constraints. So as you might know, when you work with WebGL, you have to kind of give it a near and a far clipping plane so that it knows which triangles that you try to process it can ignore safely. We can control that aspect with the clipping distance, which is this second property I'm modifying. And we can also control, independent of WebGL, it's nothing to do with it, the altitude that we want to constrain the camera to. So here I can zoom out all the way to 50,000 kilometers, go in as close as I would like to. Now let me apply these constraints. So you'll notice that I can't go further than 30 kilometers now, and no closer than, 30,000 kilometers, and no closer than 10,000. Additionally, I modified the clipping distance, and to demonstrate you this, I'll try to zoom in to this line here, and you see that the near clipping plane kicks in and removes triangles from that line that were previously smoothly rendered. Right, and the view padding that I mentioned before allows us to focus on a subsection of the view. So this is, as I mentioned, good if you want to integrate it with, say, DOM elements on the left side or on the top side, so that you can scale the view down to the size that you require, so that it doesn't interfere with your custom elements there. All right, and the quality profile and quality allow you to control how the view is rendered. So we have a couple of properties there. The quality profile by itself is like a catch-all. We can control high or low quality, and it will tweak certain parameters for you to make it faster or better looking. We also have the ability to control these aspects individually, so we can say that the quality on the atmosphere should be either low or high. We can enable or disable shadows through the lighting property of the environment, and also turn off and on ambient occlusion. So in this example here, on the left-hand side, I have a low quality view, while on the right-hand side, I have a high quality view. And it's not so easy to make out at this perspective, but for sure you can see the shadows, and you can perceive that the rendering is a bit smoother. The base map down here in the left-hand view has a lower resolution, so we require less network and traffic, and also less rendering, number crunching for the base map. Also, the models might come in at different quality or resolution with these settings. Okay, let me start an animation here to kind of demonstrate the effects of the atmosphere quality setting that we selected. Excuse me. The atmosphere or difference in atmosphere rendering is probably best perceived if I zoom out a little bit. Yep. So these are the toggles that we expose in the API for you to choose which kind of visualization quality you desire for your particular use case. All right, then now that we covered the basics of 3D, I would like to go on and show you how to add custom graphics. So for today's session, we decided that we would like to visualize tectonic plates and boundaries, and we found a data set that was the result of a study conducted in 2002, and that data set was published in GitHub and readily available for us in JSON, so that we thought it would be interesting to see what we can do with it. If you look at the data, then here's a short snippet of how the plates look like. You see that it looks similar to how we classify things at Esri. So we have features, and those features have properties, and those features also have geometry. That geometry in this case is a polygon, which is basically an array of coordinates. So let me show you what I would need to do to load that data set manually. Because sometimes we want to load data and add custom graphics to our visualizations that don't necessarily live on a feature service or in another well-known location. So we just pull it in from disk or any other source that you desire to pull it from. To do this, I can use a graphics layer, and this graphics layer, in this case, I tell it to put all the stuff that I put in it, all the graphics, to put it on the ground. So the elevation should basically be equal to the ground elevation at that point. And I add that graphics layer to my map, and this snippet you might have seen before. I create a scene view and add my map, specify which container, like which div DOM element I want to use for the visualization. Okay, so the snippet shows you how to pull in that data. We use Dojo text here to get the text representation of that JSON. We get that string basically as this variable here. We parse it, and then we have our JSON representation. And then I iterate over all the features that I found in this plates data set that I showed you before. I create a new polygon geometry for each feature. Spatial reference for this data set is WGS 84. So that's what I specify here. And then the rings property of the polygon constructor basically holds the array of coordinates that we want to have this polygon to possess. So I can just pass in the feature geometry coordinates that we saw before. So which is pretty neat because this JSON data set is like very compatible with our system. This is not so interesting. I assign a random color to every polygon that I create, and I choose to use a symbol, namely the simple fill symbol, and assign the color that I created here, and the outline should be white with a width of 1. And then I create this graphic, this custom graphic that I want to insert into the graphics layer, assign the polygon geometry to it, and use the simple fill symbol that I just created before. Add this to the graphics layer, and when I do all of these things, then I get these tectonic plates that you can see here. All right. And with that, I would like to hand it over to you, yes, Sam.
Thanks. So what I'm going to show you now is a bit more of the kind of the advanced customization that you can do and to make visualization in 3D, which are otherwise not really possible or are kind of hard to get. And we do that in the context of this tectonic plate visualization. I should say we are not geologists, so if I say something that like is not actually proper terminology or something, please forgive me. You can correct me after if you would like to. So the first thing that I wanted to do is to understand a bit more this data. So this is GeoJSON, and we can import that into ArcGIS Online, which I did. So you can just do add item from my computer. You select the GeoJSON file, it will upload it, and you get a hosted service back. And then I started just to add these layers into a web scene in the online scene viewer. And I choose a nice base map to visualize a little bit. So what you can see here now is the different plate boundaries, the origins, and kind of explore the data that they published to get a sense of what we can visualize. So if I look at, for example, so they call it the steps. They kind of discretize on the boundary and give you some attributes to look at. So let me just get this one. So they will give you things like the orientation of the boundary, the velocity of the plates, and stuff like that. So this was kind of like the maximum kind of visualization that was interesting that I could get by just configuring layers in the scene viewer, applying some renderers and stuff like that. But that's not really exactly, like I want to do something more with this. So let's have a look. So what I like this is this kind of visualization which has like a little chunk of the earth, and then you can see kind of the plates subducting, and you have like little details like the mountains and kind of a slice of the earth. So that's kind of the visualization that I wanted to create, and I will show you step by step how I went about doing that. So first, it's just going to start very basic. So I'm going to show you the visualization. I'm going to show you the code, but I'm not going to explain all the code in detail. There's too much code to really explain everything. I will explain small stuff, but then all the code will be online. You can look at it, and you can also ask me questions afterwards if you would like to. So the basic setup will be a local scene with a clipping area. That's how we get kind of a small chunk of the earth. We're going to use satellite imagery base map, just add road elevation, and then we'll add the boundary of the tectonic plate as a simple line. So I have it open here, and it's kind of the basic result that you get. So I just have a local scene. This is all very standard, right? So I have a line here, it's clipped to the local scene, and I have some elevation data and a base map. So this is a good start, but some of the things, so I would like actually that these mountains, they should pop out a little bit more. And if you have visited the custom layer session, this has probably been mentioned. So what we can do in that case is to exaggerate the elevation layer by creating a custom elevation layer and then fetching the original tile and kind of multiplying the values by some number. So that's what I did here. The other thing, what is nice, and this is a sample on the SDK that you can look at, and I don't know if maybe Jan showed this, but you can blend multiple layers together pretty easily by creating a custom tile layer. In this case, I used the hill shade layer to kind of accentuate basically the slopes of the mountains. So let's have a look. I think this recompiled. So now you can see, I mean, the effect is a little bit subtle, but the mountains, they are twice higher now than they realistically should be, which is fine for the visualization that I want, because I want kind of this infographic feel to it. And so, yeah, the shading, it looks a bit better. It's a bit hard to see, I think, also on the screen, but if you do side by side, actually there's more detail to see now. So that's basically where we start. There's nothing, I mean, there's a bit of customization of the custom layers, but nothing really specific to 3D so much. The second thing that I always like to do when I create these applications is have a little 2D overview map. So when I look at this, I don't really know where I am in the world. It's a bit hard to see. So let's add a little overview map. If I go here in the application, I have a bunch of functions, so I will show a little bit. I tried to make everything kind of in classes and in the style that we do it in the JS API, so you can also get kind of a feel of how we develop things. It's just a map view with the vector-based map, and it also will render this boundary line. It's very basic things. So let's have a look. It takes a little bit of time to load the vector tile, but basically that's now the area that we're visualizing. So now we have a kind of sense of where we are in the world. So I'm actually visualizing the plate that crosses the Himalayas. So for the next step, I wanted to do something that makes this more like an infographic kind of style. And so what I want to do is to show a title and a little description of this application or this visualization. And I actually would like to do this with the DOM, because it's much easier to just add some text and to style it, and you can use CSS. But at the same time, I would like this to be integrated into the 3D view. So this is kind of a 2.5D visualization, right? Because the DOM doesn't actually integrate with WebGL, so it's either in front or in the back. It cannot be like crossing through the mountains or things like that. But we can actually use CSS transformations to make it appear as if it's actually being set in the 3D perspective. So let's have a look how that works. I created this class that does this because I thought maybe it's useful if people could reuse this. I called it DOM element 3D. Should probably have called it 2.5D, but it's okay, I think. DOM element 3D. The most important thing is this function. So what I give it is a map location. That's where I want to position it, and I convert that map location to a screen position by using this toScreen method that Thomas already talked about. And then I will just compute some translations in screen space to center that element on that screen location. And now the interesting part is here, where I use the heading of the camera to compute the rotation around the Y CSS axis. And I use the tilt of the camera to compute the rotation around the X axis in CSS. And then I'll use these CSS translation and rotations to get and I assign it to the style transform, so I get very quick updates, right? If you know that like these style transforms, they kind of translate directly to, I don't know exactly how they do it, but probably directly to the GPU. They don't have to recompute any layouting and stuff like that. So that's a good way to do that. So let's have a look if I enable this. I'll reload my application. So the thing that I added here, so I added this title tectonic plates, I added the little description that you could see in the slide, and you can see that it actually looks like it's part of the 3D scene, while it's just DOM, right? So you could put anything in here, graphs or images or stuff like that. So it's a nice way to enhance your visualization without having to do complicated WebGL programming. And you can see it's very reactive, it really integrates very closely. Then of course, if you do things like this, it also doesn't look very good. But that you can solve. I mean, I just made this for a demo, right? So this starts to look already pretty interesting to me. So there's a bunch of customizations here. Let's see what else we can do to make this better. So this boundary here, I like that I can see where the tectonic plates would be, but what I'm also interested in is like, what is actually the elevation profile? Like if this subduction would cause these mountains, of these mountain ridges, maybe it's interesting to look at the profile of the elevation. There's different things that you could do to visualize this. I thought it would be interesting to try to integrate this into the 3D scene as a kind of wall strip that shows the elevation profile in 3D. There's two new things that we're introducing in 4.7 that makes this possible to do, and I will briefly introduce them. The first one is elevation sampling, and the second one is the custom mesh geometry. So elevation sampling, we already had this query elevation, if you have seen that on the elevation layer. This allows you to go to the service, request elevation values, and then, so you give it a geometry, and then it will give you back a geometry that has Z values at the XY positions of each of the vertices of that geometry. In 4.7, we now also expose what we call elevation samplers. And these allow you to create kind of a sampler for a specific extent of the service. And then you can synchronously sample the elevation sampler at any point within that extent. And we'll interpolate the values for you. This is very nice because then you can just fetch once and then very interactively start sampling. The other thing that we've done is to expose this on the ground view of the view. And this allows you to sample directly the surface that we are actually displaying synchronously. So you don't actually have to fetch anything. We just use the data that we already fetched to sample. The mesh geometry is a new client-side Esri geometry for 3D shapes. It's a general triangle soup representation, so it's vertices and faces that make up triangles. It's relatively low-level kind of geometry, so there's some effort involved in using it. But I have a small SDK sample that I will show you. It supports normals, textures, multiple components, and materials. And you can use it with regular meshed symbology, like mesh symbol 3D and fill symbol 3D layer that we already have for things like the scene layer. So I'll very quickly show just a sample that I created that will be available in the 4.7 SDK. It's kind of a little bit of a toy sample. We'll probably make a slightly better sample for before the release. But this is just to show you kind of how you can create, with simple shapes, custom 3D geometry that you can then place in the 3D scene. So here it's a snowman without arms, but he's a bit of a poor snowman. But there are some trees here that it kind of exposes all the different simple utilities that we provide. So this, for example, a linear gradient that we render on the canvas, and then we apply it as a texture. So yeah, if you're interested, you can once the SDK is out, you can have a look at this sample. So that's the two pieces that we need to create this kind of wall. So we sample the elevation of the ground view, and then we extrude it out, and then we create vertices and make them into a mesh geometry. So let's have a look. I have to find back actually where it is. Oh, yeah. So I have this layer which renders this line, and it will either do the simple one that I showed you, sorry, or it will do the more complex mesh one. So I just switch this out to create the mesh variant of this. I'll quickly show you a little bit. So this is just a mesh symbol. I will use edges. That's the new feature that you've probably have seen to make a kind of outline so it pops out a little bit more. And then I have this layer here which renders that mesh. I give it the ground view elevation sampler. I will give it the height. So actually if I change this, it would extrude more or less. If I look here, there's some stuff going on. Mostly, this is the interesting function, create path geometry. It will create this mesh from a polyline. So what it does, first I clip the line that I get. So this is the plate boundary line, right? It's the line that goes all the way the place, but I only want the part that is currently being clipped with the clipping area of the view. So this is easy. We can just use the geometry engine. We clip the line against this clipping area, and then we get the clipped line back. Then I want to densify the line. So the line will, because this line is kind of discretized at a low resolution, I will probably just get one single line segment if I have a small clipping extent. Then I cannot really make an elevation profile out of that. So I will use the geometry engine again to densify the line. I will have a fixed resolution, I think at like approximately 50 segments along the clipping area. After I identified the line, I'll use this elevation sampler, which is the one from the ground view, and I will just query elevation for that line, and it will give me back the line, but now with the z values of the ground. And then I create the extruded mesh from that. The extruded mesh like I will not go into too much detail here, but basically you have to provide the vertex positions of all the vertices of the mesh, and then specify which of those vertices make up triangles, and that will actually create the 3D geometry. So this is the mesh class. It's not so difficult to understand, but it's a little bit difficult to fit all the pieces together if you haven't seen it before. So that's basically all there is to making that strip. So let's see if that actually works. Okay, so now we have this kind of 3D elevation profile that we can see kind of what the elevation along this boundary is. I extended the line a little bit beyond the clipping area here. I don't know, maybe you've seen that in the code that I showed you, to get a kind of idea of where the boundary is intersecting with the clipping area. And you can see the edges here. This is the white edges along the mesh geometry, and I made it slightly transparent to get a kind of nice look for it. Okay, so what's next, or what's left to do? So what I want is to render this kind of like these layers of the Earth, right, and the tectonic plates, and kind of indicating the subduction. Because here really we only have this like the ground surface right now. So what I can do is, again, using the mesh geometry, I can actually render that as a box, basically that will represent this kind of well, let's say, okay, at first I render a box basically around this, so I get a nice kind of cake look, or I don't know how to say it, like a slice out of the Earth. And then I'll use the data to create the subduction plates in 3D using the same mesh geometry by tessellating it such that it looks like I have the plates. I will show you first how it looks like. So this is the kind of the look that I was looking for, more or less. So I have this slice through the Earth, and these are basically the plates. And I use the data of this steps feature service that I created to calculate some properties of the plate activity there. In this case, I kind of use the angle to indicate how like collinear the plates are moving. And I kind of use the length of this to indicate the speed. I didn't put any absolute values in here, but that's kind of the look that I was going for. I use some textures here to kind of indicate that this earth and stone or dirt or soil. So that's kind of pretty. It's not exactly like this, obviously, right? I only had so much time to spend on this, but it's coming in the right direction, and it gives you kind of the idea of what you could do. So in terms of the code, we can have a little look to see how this works. So I have the same kind of thing. There's the mesh symbols. I use the ground elevation profile, or the ground elevation sampler, because as you can see, I would like to really match up this slice with the elevation. And so I'll basically sample along the edges of the clipping area and then make up the mesh. If you would look at the triangles, there's like little slices here that make up all the triangles of this mesh, and there's triangles here and there. So that's like a little bit cumbersome if you think about it to set up all these vertices, but it's definitely doable. There's other ways to generate this, so you could also use external editors to generate meshes, like you use either Blender or any of these programs and make OBJs and import them. So I also made the layer for this. It's just a graphics layer, and I subclassed it like this, and then I just add graphics to it. There's a bunch of stuff going on, so I won't go into too much detail here. This is the part that creates the kind of the slice of the earth of one side. In the end, it will create again a mesh geometry with positions, UVs for the texture mapping, and indices that make up the faces. I understand this, like it's maybe hard to understand how this mesh geometry exactly works from this. but you will be able to find out once the SDK is published. We'll provide small samples, snippets, all the utilities, etc. All right. So what more could we do? So I like this. Well, I kind of like this visualization as it is, but I can only see really one part of this really large tectonic plate. So what I would like to do is now, this is a static visualization. I cannot really interact with it, but what if I could actually slice through the tectonic plate now? So that's what I would like to do. And basically what we can do, so what we have to do is control the camera, and we control somehow how we slice through the things. So let's have a look. I'll maybe first just show you again what it does, and then I will try to explain how it works. So what I did is I basically went in and I used the mouse events on the view. And then when I scroll, I'll use that to kind of alter and travel along a path. So when I scroll now, I basically go through the slides of Earth. And you can see here on the 2D overview, it's following me around, so you can see where I'm located. And you can see it's kind of orienting the camera based on the direction of the path. And then it's slicing through the Earth. I always see kind of the same kind of slice. So the other thing that I want to do, because sometimes you say, okay, I actually want to look at it from this direction, and then I want to start slicing again. So it will kind of remember how you looked at it, and then based on that, relatively travel along the path. You can see also here that now that I have this traveling, I can actually see that this tectonic plate here is updating while I'm visualizing this. Okay, so let's have a small look. Let's have a look at how we can implement this. There is kind of two things that need to happen. The first is, let me go right here. Sorry. The first thing that we need to do, I have a kind of helper class called the viewport that determines or calculates the clipping area. But you can imagine that to get this visualization, what you need to do is I want to change the clipping area to a different location, right? So I see a different piece of the world. If I would do that and I don't change the camera, what you would see is that when I scroll, kind of this slice of Earth, it kind of travels away from me, so it kind of escapes. So I have to move the camera in a consistent manner with that change along the path, so that it actually looks like that slice always stays in the center of the screen. So that's what I did. To make this look kind of nice, like you have smooth animations. If I would do it just along the path, it would look very blocky. It doesn't really integrate very well. So a common way to solve that is to use piecewise interpolation of the path. One of the most used methods is called Catmull-Rom interpolation. I made a class for that interpolates this. Basically what you get is just a smooth curve out of that, and you can interpolate this. So I passed in the polyline, and it made a piecewise interpolation out of that, and that's basically this class that you could have a look at it once it's online. Sorry. So to move along the path, what I do is I just sample. So I increment this position on the path, which is just going from 0 to 1, interpolate the path that is smoothed out by this piecewise interpolation, and then I set here I call center of the viewport, which basically calculates the clipping area, gets set on the scene view, and it will change that. The second part would be to update the camera. What I do here is I have a function that uses the same path to calculate the heading of that path, so the direction in which it's traveling at the current position at what I'm looking at. It does this by just sampling around the point where I'm looking at, and then doing a kind of like a 3-point average of the path. So this gives you the direction of the line at the position where you're looking at it, at the center of the view. And then it's just a matter of, so I use goto. I basically use the center of this clipping area as the center, like the target. I have a fixed scale in here, so I always keep the same distance to that center. And then I set the heading So basically that is the orientation of the camera, right? And doing these two things together exactly correctly gives you this illusion of looking at the same, like a block, and you slice through it in time. So there's no real special things going on here. I just use only the clipping area and the camera, right? But in a consistent way, so it looks like I'm doing that like that. All right. Finishing touches. So I was already pretty happy with this as a demo to show the new capabilities, but I want to do a little bit more to get kind of closer to this visualization. And I thought it would be nice to have animated lava in this demo, just because we can, right? So obviously it's not really realistic. There's not like lava just under like 100 meters under the earth, but like here it's a kind of infographic, right? So that's the idea. To do that, so we don't really yet, as of yet, we don't support natively having like these kind of animations that I would like this lava in the SceneView or in the API. What you can do is make use of the external render interface. So this external render interface will give you very low-level access to rendering additional stuff in the 3D scene. This you can use if you have data that you cannot visualize by conventional means with renderers that we have available or other methods. So the mesh geometry will give you another like officially supported way to do 3D geometry in the scene that you couldn't do before, but there's other things like these animations that you can do. You have to be really familiar with WebGL if you use this. You have to be able to afford that development because there is not a lot of support from us. If you want to do this kind of stuff, you're kind of on your own. So you have to really render with WebGL by yourself. This is what we call an experimental interface. There's some samples on the SDK, some simple samples to get you started if you're interested in this. So these are turning windmills. They're based on live data. So they run at that speed of the data. This is an example that I showed at the last Dev Summit. If you were there, you might have seen this. It's available online if you want to look at it, the same presentation. This is using WebGL to render wind velocity by simulating particles on the GPU. All right, this is the basic concepts in API. It's actually a pretty small API, it's external renderers. You have a setup function and a render function that gets called every frame that we render. The context has a WebGL context, render camera, there's a bunch of other stuff. Those are the most important ones. And reset WebGL state is actually quite important. I won't go into the details, but if something doesn't work and if you don't do this, then many things won't work. So please do that if you use this interface. All right, let's try and add this now. So I'm gonna use WebGL to render this kind of lava that I wanted. So let's have a look where I enable that. So I call it lava render. Again, let's have a look first at how it looks. All right. So this is kind of the thing that I wanted. It's animating, as you can see. It's moving around. It's not very realistic, obviously, but it gives a kind of nice additional touch to this visualization. I'm pretty happy with the end result like this. So let's have a look at how we can actually implement this now. Let's have a look at this lava render. It's again a separate class. I can actually pause the animation because this is going to render over and over, and my machine is probably going to be not so happy with it. So I can just pause it with spacebar. I use again just key events on the view. The external render interface. So here, like I said, this is really like this is as low as you can go, right? This is like you have to just do all the work yourself. So you have to set up all the WebGL state, use the right blending, depth testing. You have to set up all the uniforms for your shader. If you're not familiar with WebGL, everything that I say doesn't make sense to you, but I'm not going to explain it in this presentation. I don't really have the time. But if you're interested, either you can look online, look for that, or come talk to me and I can explain things. We set up buffers and vertex arrays. So if you're familiar with WebGL, this sounds very familiar to you. So basically what we render is just a box here. how to get the lava. So what I did is I didn't really want to spend the time to really make this myself. So I just went to ShaderToy. If you know this website, it's really amazing what people do on there. So all this thing is rendered procedurally on the GPU. I looked for a shader and then I just took it and adapted it. So the code is, I didn't write the code, so I can say it's really unreadable. But yeah, so it doesn't really matter all the details in here. But the idea is that you get a time variable, and then you add some noise and some stuff, and then you get this kind of visualization, and you animate it over time. So the important part here is not really the exact details of the animation. It's more to give you an idea of what it takes to add these kind of additional visualizations on top using WebGL. So it is kind of like the mesh geometry in the sense you have to set up the same vertex attributes. We have some utilities to convert from map coordinates to render coordinates and stuff like that. But that's, yeah, I mean, like I said, all this stuff is going to be online, so you can look at it on your own time if you're interested in that kind of thing. So that kind of concludes this visualization. So that's where I kind of stopped playing around with it. And yeah, that's it. Are there any questions? Or is everybody waiting to go to the party? Yes? So the question is if we are going to keep supporting these external renderers in the upcoming versions. So the answer is yes, but so there is a but because so I don't think we are going to lift the experimental support for this. Because the thing with the external renderers is if you do one thing wrong, like you mess up the state, you could actually mess up all our render state and you don't see anything. And it's really going to be hard for our support to then come in and say, if you have this problem, like how are they then going to solve it? The other thing is that we want to be able to make certain changes to our internal rendering pipeline that might affect the external render. So one of the things that happened in recent releases is that we've added a more complex lighting model. But the external renderers still get exposed kind of a simple version of that. And so some of the lighting has changed a little bit, or the way that you have to interact with that. And we want to keep that freedom. We need that freedom actually to keep our pipeline modern and up to date and performant. So, but this interface is not going to go away. Yeah. Any other questions? If not, then thank you.